Hi everyone, welcome to part 3 of chapter 13. This is our lecture on solutions. Last time we left off, we were talking about the solubilities of gases and of solids, in particular liquids. And so today we're going to start assigning some ways to mathematically calculate how much of our gas is dissolved in our liquid or how much of our solid is dissolved in our liquid. So that's what we're going through today. So the first bit we are going to talk about is Henry's law. And so Henry's law talks about the solubility of a gas in a liquid. And it says the solubility of a gas is directly proportional to its partial pressure. So the higher the partial pressure, the higher the solubility. And then we have this Kh value, that's the Henry's law constant, and it will be different for different gases because, some gases dissolve better in particular liquids than others. So in here over on the right, we have table 12.4, and that's showing you, this is from a different book, but it's showing you the values for how well the gases dissolve in water at 25 degrees Celsius. Obviously, if this temperature were higher or lower, then the gases would dissolve, more or less. So we have different constants for different gases and at different temperatures. So really, this only works at room temperature for water with these values. So let's go ahead and figure out how we would use this. So here we are. What pressure of carbon dioxide is required to keep the concentration of carbon dioxide at 0.12 molar in soda at 25 degrees Celsius? So like we talked about last time, right? If we, decrease the pressure, if we open our soda can, then the, carbon dioxide can leave. So it's asking, what pressure is required to keep at least a decent, a decent amount of carbonation. So our equation is S gas equals Kh times the pressure of our gas, right? This is the partial pressure. And so we have, so here we're trying to solve for pressure. So we need to rearrange this, right? The pressure of our gas is going to be equal to the solubility of our gas over our Kh value. And so solubility, whenever we're talking about solubility, this is given in molarity, right? So if we look at our constant over here, right, we have molarity per ATM. So we need to make sure that our solubility is always in molarity and our pressures are always going to come out in atmospheres. So here we have our molarity, it's given above, 0.12 molar. And then our Kh value, so here we're looking for carbon dioxide. So that will be this value. So we have 3.4 times 10 to the minus 2. And again, this is molarity per ATM. So if we go ahead and calculate that out, we'll get the pressure that we need is 3.5 atmospheres. So, 1 atmosphere, right? Taking the lid off, not going to cut it. We need 3.5 atmospheres to keep our molarity at 1.2 molar. So we can also figure out how many grams, of a particular gas might dissolve at a given set of, pressure, temperature, and things like that. So this one says, how many grams of ammonia will dissolve in 0.10 liters of solution when its partial pressure is 7.6 torr? So again, our equation that we're working with, S gas is equal to Kh times the pressure of our gas, right? And so here in this particular problem, right, we're solving for grams, which means that we're going to need to find things out about moles, and we're going to go through this by solving for our solubility here. Because we have for ammonia, we have our Kh value, that's a constant, and we are given a pressure, but our pressure is in torr, and we need it to be in atmospheres in order to use our constant. So let's go ahead and we will shift our 7.6 torr. And we know that for, 760 torr is 1 ATM. And so that will get us 0.010 ATMs. And we can go ahead then and calculate the solubility of our gas in molarity, right, by plugging things in. So we have 5.8 times 10 to the first molar per ATM. and we have 0.010 atm, which gets us a solubility of our gas of 0.58 molar, right? And we have a volume here. So we have our molarity, we have our liters, which means that we can rearrange our molarity equation, right? Molarity is equal to moles over liters. So we can rearrange that in order to solve for moles. So we can do moles equals molarity times liters. So our molarity is 0.58 molar times 0.10 liters will get us 0.058 moles of ammonia. And then, of course, we can go ahead and convert our moles into grams using the molar mass. And there you go. So that would be how we would combine, our molarity equations, which we know and love, with our new Henry's Law equation. So on to liquids. Liquids or solutions, right, will often have variable compositions. We can describe them mathematically, which we will spend a lot of time doing, but we can also describe them just kind of relatively. Right, so we can use these terms dilute and concentrated to talk about whether there is a lot or a little bit of our solute in our solvent. So concentration, just in general, is the amount of solute in a given amount of solution. So in the previous examples, we were looking at our concentrations in molarity, right, moles per liter, which is a really common way to talk about concentrations in chemistry. But these solutes can be in they can be gases, or they can be solids, right? And we're typically dissolving things, though, in a liquid. So concentration is the amount of your stuff that you have managed to dissolve. And we have lots of different ways of talking about concentrations. So one way, just kind of relatively, is talking about them with the terms concentrated and dilute. Typically, if we have, a stock solution, we're going to buy these stock solutions really concentrated. It's cheaper that way. And then you can dilute them back in your lab to whatever concentration you feel like diluting it to. Rather than buying, 1 molar hydrochloric acid, we would buy concentrated hydrochloric acid and dilute it down. So concentrated, if your stuff happened to be colored, right, you can tell that it's more concentrated because, your solution would be darker. It has these dark solute particles that are all really close together. So if it has a color, a tint of some kind, then concentrated solutions are darker, and dilute solutions, because you've added a lot of water, typically, we've diluted it down, and it will become lighter in color because now your solute particles are farther apart. Obviously, most times in chemistry, we have nice clear liquids, right? Everything looks like water. So this isn't the best way of analyzing whether something is concentrated or dilute. If it's a clear solution, that wouldn't give you any help at all. But we use these terms to talk about amount of solute particles versus solvent. So if you have a lot of solute particles per amount of solvent, then we have a concentrated solution. If we have very few solute particles per amount of solvent, then we have a very dilute solution. And then, anywhere in between. So concentrated, lots of solute, very little solvent. Dilute, lots of solvent, not so much solute. But we have better ways, right? We have lots of other ways to talk about concentration. The most common one, like I've said, in chemistry tends to be molarity. We're going to use molality quite a bit in this class. We'll also use mole fraction, mole percent, and we have all these other ones, part by mass, percent by mass, parts by volume, and we're going to go through how to do some of these calculations. The big ones for this class are probably those top three: molarity, molality, and mole fraction. So our first one, these are example problems and practice problems. If you like, at any time, I'm not going to keep saying it, but if you want, you can always, pause and try it out before just seeing the answer. Or if you would rather watch me do it, and you can try ones on your homework or, on the lecture worksheets, that's fine too. Either way, so a solution is prepared by dissolving 43 grams of potassium chlorate in enough water to make 100 milliliters of solution. What is the molarity of potassium chlorate in the solution? So the first thing we would need to do, right, we know molarity. Molarity is moles over liters, and more specifically, it's moles of solute per liter of solution, okay? And oftentimes, and we've talked about this before, oftentimes this liter of solution is the liter of solvent. A lot of times, not always, just be careful. But a lot of times it is, because the amount of space that's being taken up by our solid is usually not very much. Sometimes it is, sometimes it's not. So just kind of pay attention to things. But the first thing we'll need to do is take our 43.0 grams of potassium chlorate, and we will need to turn that into moles using the molar mass. So I've given you the molar mass there. So there you go, 0.351 moles of potassium chlorate. And then after we have calculated moles, we can do molarity is equal to our moles of our solute over our liters of solution. So we have milliliters, right? We'll just go ahead and convert that real quick to liters, right? We divide by 1,000. That will give us our liters of solution. And we get our molarity, 3.1 molar, 3.51 molar potassium chlorate. There you go. So there you go, not too bad. Take your grams, convert them to moles, divide by liters, off you go. This is a really easy problem. It's a really straightforward problem. Nothing that exciting about it. So this problem is weight percent problem. Okay, so weight percent is going to be the mass percent. So if we go back and we look here, the percent by mass. So there's a lot of different terms that this goes by. Weight percent is one of them, mass percent, percent by mass, all of that kind of stuff. So the way that we're going to calculate this is going to be the mass of your solute over the mass of your solution, so total. So your mass of your solution will be the mass of your solute plus the mass of your solvent. Whereas I talked about, in molarity, a lot of times our volume of solution is just coming from our solvent. The mass of your solution, we're always going to add them together. And then it says you're going to multiply it by a multiplication factor, and it depends on which one of these you're doing. We are doing percent by mass, and that percent tells you you're going to multiply it by 100. Okay, so going back to this, our weight percent, so our percent is going to be our mass of our solute over our mass of our solution times 100. Okay, so this says, what is the weight percent of nitric acid in 3.26 molar nitric acid? So that might be a little bit tricky. You're like, well, I don't have the masses of anything, right? That doesn't help me. But just remember that in this 3.26 molar, right, that means 3.26 moles of nitric acid per 1 liter of solution. So that's telling us we have, if we assume, right, in these types of problems, we can assume we just have 1 liter of it. So if we just have 1 liter of our solution, then we have 3.26 moles of nitric acid. So then, if we know, how many moles we have, we know that for every, 1 mole of nitric acid, it's given to us, that molar mass, 63.018 grams of nitric acid. And we say, okay, we'll calculate that. All right, we have 205 grams of nitric acid. So that is the mass of our solute. Again, we just assumed we had 1 liter of solution. And I would do this anytime you have molarity. Assume you have 1 liter of it so that you can use that molarity as your number of moles of solute. Makes your life a little bit easier. So now that we assumed we have 1 liter of solution, we can use our density, right? This is actually, sorry, I should specify this. This is the density of the solution, right, of nitric acid. So then we can use this density to figure out how many grams of solution we have. So if we assumed we had 1 liter of solution, and we convert that to milliliters, right? 1 liter of solution would be, 1,000 milliliters of solution. And we can use this density then to convert from milliliters to grams. Oh, that should be an L. So we get 980 grams of solution. So now we have the mass of our solute, we have the mass of our solution, and we can go ahead and we can calculate our mass percent now. So we go, okay, our mass of our solute is 205 grams. Our mass of our solution is 980 grams. And if we multiply this by 100, then we will get 21% nitric acid. That's how we report percent by mass. So we just put the percent and the percent of our solute, right? Never of the solution. So 21% by mass nitric acid. That would be our answer. So that would be how you would convert molarity into mass percent. Let's try another one. Mass percent problem. So now we have 2.489 grams of cesium oxalate are dissolved in enough water to give 265 milliliters of a solution whose density is 1.0528 grams per milliliter. What is the percent by mass concentration of the solution? And this one, even though I put it after the last one, this one is actually an easier problem. And I think you can see that fairly straight off. So, but again, mass percent is going to equal our mass of our solute over the mass of the solution times 100. So we have the mass of our solute. Done. And then we know some things about our solution, right? We have our volume of a solution, right? And we have the density. So if we have the volume and the density, we can convert that into grams. So we have 265.0 milliliters. And for every 1 milliliter, we have 1.0528 grams for our solution. So we get that we have 279, sorry, I don't have my sig fig on that. 279, we'll say 0.0, I don't know what it is right now, grams of solution. I didn't write it down when I worked this out. And so then we can have our 2.489 grams of our solute over 279, again, this might not be 0.0, but we're going to go with it, 279.0 grams of our solution times 100, and 0.892% cesium oxalate. Say that's a 0 too. Sorry about the oxalate. Sorry about the sig figs on this problem. Should be 4 in your final answer, so this might not be quite correct. But there you go. There you have it. So we already had the mass of our solute. We used our density and our volume to find the mass of our solution. Divide them up, multiply by 100, and you will get your answer. Let's try this one. Mole fraction. So we've talked about mole fraction a little bit so far. Let's go review looking at this. So mole fraction is up here. We use the Greek letter chi for that. And it's our moles of solute over our moles of solution, so total. So solute plus solvent. And you're not going to have any units on this. We've talked about that before. Mole fraction, we don't have any units because essentially moles over moles cancels out, so we don't have anything left. I mean, we're not multiplying it by anything, so it's not a percent. So we have no units on our mole fraction. So this one says, calculate the mole fraction of acetic acid in a 27.13 mass percent solution. So we have our molar mass of acetic acid there, answers given. So what we need to do, if we have 27.13 percent by mass, aqueous solution, which means 27.13 grams of this, right, is acetic acid. If we assume that we have 100 grams of our solution, right? So whenever we use percent, we're going to assume we have 100 grams of solution. It's just going to make our math easier. So if we have 100 grams of solution, then we can use this, this percent as an amount in grams. So that's how many grams of acetic acid we have. And it tells us it's an aqueous solution. So if we have 27.13 grams of acetic acid, if we did, 100, right? And I'll include some sig figs on here. If we have 100 grams of solution, I don't know why I keep doing that, solution, minus our 27.13 grams of acetic acid, right? The rest of it then is water. So we would get 72.87 grams of water. So now we have grams of acetic acid, we have grams of water, and we can go ahead and calculate the moles of both of those using the molar mass, and then toss that into our mole fraction equation. So 27.13 grams of acetic acid. And if we use the molar mass for that, 60.054 grams of acetic acid. And 1 mole of acetic acid. That gets us 0.4518 moles of our solute, acetic acid. So then we can do the same thing with water, right? We have 72.87 grams of water, and we'll use the molar mass to figure out how many moles. All right, so now we have moles of our solute, and we have moles of our solvent. So be careful, right? So when we have our mole fraction, we're going to do moles of solute over moles of solution, which means we're going to have our moles of our solute over our total moles, right? So that's moles of solute plus moles of solvent. So be very careful you don't just divide one up over the other. So we'll put 0.4518 moles on the top, and then 0.4518 again on the bottom, plus now our moles of water. And that will get us our answer, 0.09356. Sorry, running out of room. But that would be our mole fraction of acetic acid in the water. Again, no units on that answer, just divide them up and report your answer. And that's it for today. So a couple different ways of, saying how much stuff, right? How much is dissolved in our liquid. So we talked about how to talk about gases, right? How to report gases solubility in liquids. And then we talked about how to report solid solubility in liquids. So today we talked about molarity and mass percent. And mass percent is very, very similar to parts per million. Actually, we'll go back and we'll look at that real quick. The way that you would do parts per million or parts per billion, because you'll come across those when you're doing your homework, they're going to be exactly the same as we did percent by mass, except instead of multiplying by 100, you're going to multiply by a million, 10 to the 6th, or a billion, 10 to the 9th. Otherwise, it's exactly the same. And parts by volume is essentially the same as parts by mass, except you're using volumes instead of masses. So it's pretty much exactly what it sounds like. Mole percent that we didn't talk about yet. Mole percent is your mole fraction multiplied by 100. This is not really common. Pretty much nobody uses mole percent. We use mole fraction a lot. It's very uncommon we use mole percents. And then the one we didn't talk about today is molality. And we will talk about molality in its own separate lecture, because we use molality to talk about colligative properties and freezing point and boiling point and all that kind of stuff. So yeah, today was more just fun with calculations. So keep working on this, get some practice on reporting concentrations in a bunch of different ways, and send me any questions, and I'll see you next time.